in subcritical flow, there's backwater effects, and so those rings will perpetuate upstream and downstream. Numbers, you don't know the number, cancel it out, assume it's zero, that kind of thing, and represent all the factors that you have. You have the area of this circle. You have your change in elevation. That's your change in elevation. You have this is your gravitational constant, 32.2. And so you can get from this elevation, you can get the flow into these pipes. Now the a really good entrance condition, a really good pipe, it could be 0.7, 0.8. A really bad one could be 0.4, 0.5. You can go to a book and get those formulas. Guys did millions of experiments to figure out what the C is for pretty much everything, and that's called an empirical number. That's because it doesn't come from all sorts of mathematics. It comes from experimentation, and they solved everything and came up with some good C values here. That's the only empirical part of that formula. Now there are several other formulas that are derived or semi-derived, and that one is for orifice flow, getting water into an orifice. And almost always that orifice flow is going to dictate how much water you're going to get through that pipe. That pipe could be at a great slope, but usually the dictating factor is entrance condition, how much you can get in there. Another big one that we use all the time, and we'll skip the mathematics. Let's just go flow over a weir. Flow is equal to CLH to the 3 halves. That's flow over a weir, usually a sharp-crested weir. And a lot of this has been derived from Bernoulli and from equations. When you see these really nice exponents and things like that, you know that part of it is derived. When you come up to a coefficient, you know that's something they derived empirically. They did a lot of experimentation. So for C, on the best sharp-crested weir you could ever have, C is going to be 3.3. A normal sharp-crested weir, a normal weir in operation, so that for each any elevation regime, you can have 2 different flow depths: a supercritical depth, thin and fast, or a subcritical depth, slow and deep. And you wonder, well, how does that happen like that? And I think, in thinking long and hard about it, it brings me back to the old quadratic formula. Roddy, do you remember your old quadratic formula? It comes from that, but it's, x is equal to like minus b plus or minus the square root of
b squared
for yada 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 yada. The key here is b plus or minus. And I'm sure when you're in high school you say, what's up with the plus or minus? What it gives you is 2 answers. So when dealing with a parabola, and dealing with the parabola of this relationship, it gives us 2 answers. It gives us conjugate depths. So you can blame that on, or you can credit that to the hydraulic formula. And the interesting, so that's why in dealing with flow calculations, you have to determine whether you're in a critical zone or in a subcritical zone. Typically in nature, it doesn't stay critical for very long. There's a lot of head loss associated with that, because, Chuck, head loss was proportional to
E equals mc squared.
B squared over 2g. So it'll go critical at times, but it very quickly wants to jump back up to this conjugate depth. And the reason, and the great thing about this graph is this point right here, where there is only one conjugate depth. There's only one depth, and this depth would be called critical depth. Very good. So this is why we measure. That's why we measure that in flumes. The flow entering a flume comes in through here. We measure it at critical depth, and at the exit of the flume, it goes supercritical, eventually to get back to that area there. Are there any questions?
Don't sign up to be a professor anywhere.
All right.
So
you're done with school, aren't you?
Yes.
the total energy then changes through the whole, going through the flume then?
The energy at the flume. This is where you'd be measuring. This would be most efficient energy.
The means is so.
Right.
But yes, it's
The total energy.
It's just important to know that you're just measuring the critical depth when you're measuring in a flume.
mhm.
You're measuring the critical depth.
And in actuality, when in a weir, you're also measuring a critical depth there. They're all kind of related to that Bernoulli relationship. And Everett discussed a couple different kinds of flows: steady, non-uniform flow, or unsteady flow. What we deal with in dam safety quite a bit is rapidly varying flow. And we've only recently been able to model rapidly varying flow. What would you describe as a rapidly varying flow? Anyone? Anyone? That would be a hydrograph. That would be a 100-year flood, where that flood goes from 0 to 100 and back down to 0. Or a dam breach, where that flow goes from 0 to 100,000 and back down to 0 very quickly. And in river modeling, for years we were only able to model steady flow, one flow. But with the improvement that we've had with the computers, we're able now to put in hydrographs, whether it's a storm hydrograph or a dam breach hydrograph, and calculate and model rivers for this rapidly varying flow. And again, when modeling that, and you have to determine fairly quickly along in the modeling process whether you have subcritical or supercritical. If you're modeling subcritical flow, you start at the downstream end and work your way, calculate iteratively upstream because of the backwater effects on the downstream flows. In supercritical flow, you start at the upstream end and you work your way downstream, which is actually a little easier because there are no downstream effects on the water upstream. So, in dam safety, we deal with that rapidly varying flow quite a bit. I think I've effectively covered everything that I've sketched out here. If there are any questions, or anybody from the regional offices has anything they want to discuss, please give us a call, let us know. Everett, did you have anything else that you wanted to add? Or any questions, James? Anything else that we've missed? Do you want to do a little piece on Darcy's Law here? No. That could be a whole nother presentation. Maybe we can get James to do that someday as a follow-up to this. As we have. Chad Gorley once said to me that you make your living on two equations: the Weir equation and the orifice equation, and two models, HEC 1 and HEC 2, river modeling and basin modeling. The whole other side of the coin, and this is surface hydrology, open channel hydrology. This is the bird's eye view of the world. James deals with the worm's eye view of the world. What do we have underneath the ground and the groundwater, and how do you deal with water movement through a porous medium like that? And correct me if I'm wrong, but the grounding equation for that is Darcy's Law. And hopefully our next presentation will have James do a little groundwater modeling, and he'll break it down to equations that we can all use and come up with some estimates in our day-to-day work in the office and in the field. So I hope this was educational to you and enlightening, and thank you for your attention.